Hi, Professor. I was wondering if our chem lab exam was going to be online now because of COVID.
So my two sections, I've moved them to online. You'll have to check. I'm not certain who your instructor is for that.
I have Namani.
Yeah, you'll have to ask him if he's planning to move it online or not. I gave the other instructors the option. It's up to them. Like I said, for me, for my section yesterday and the section today, I've moved it online. The others, we're going to decide.
Okay, thank you.
Okay, we'll go ahead and get started. Can everyone hear me and see my screen?
Yes.
Thank you.
Yes.
Thanks. So today we're going to start on chapter 9, but before we get started on that, I just want to mention a few things. I've had some questions about the lab final this week. And so I wanted to tell you the status of that. So for my two sections, the one yesterday and the one today, I've moved the lab final to an online final. And so the other three sections, though I'm not certain what those professors have decided to do. So if you have questions about whether it's going to be online or not for those sections, send a message to the professor. As far as I know, they're still all planning to do it in person. There are some exceptions for some students who are having to quarantine, but my understanding is that as of now, they're planning on doing it in person. That certainly could change, but for my two sections, the one yesterday was online and the one today is online. The other three, go ahead and check with those instructors. The other thing I wanted to remind everyone about was on Monday, we'll have an exam, and that'll be on chapters 7 and 8. And that'll be the normal type of online exam. So we won't have a Zoom meeting on Monday. The other thing I wanted to say about chapter 9 is chapter 9 will be the subject of our last quiz, and that will be a take-home quiz. And so I'll probably issue that, I'm guessing Wednesday afternoon, and then you'll have Thursday, Friday, Saturday, Sunday to complete it, and it'll just be due by Monday. So that'll be the plan on the fifth quiz, which is going to cover chapter 9. Any questions about any of that stuff? Okay, so let's get started on chapter 9 then. So chapter 9 is molecular geometry and bonding theories. And hopefully some of this will look familiar to you because it's what was covered in the last lab of the semester. So once again, under normal circumstances, we would have been doing the lab the week of covering this in the class, but in an effort to try and get everything in before any COVID issues happened, we just kind of scooted things up. So sorry that it didn't coincide better, but hopefully this will allow things to make a little more sense. Okay, no idea why there's the red mark on that. So I'm going to just do something for a second here. I'm going to stop share to see if the red mark will go away. Okay. So when we talk about molecules, we're interested in how they're put together. So in other words, the bonding, but we're also interested in the shape. The shape of molecules influence how they react and give them some of their physical properties as well. So the Lewis structures, which we've been talking about, those are pretty good at showing how things are connected in terms of the bonding to one atom to another, the lone pairs of electrons and things like that. But it really doesn't give us any information about the shape. So it doesn't tell us about bond angles or anything like that. but we can use the Lewis structures as kind of a starting point to build our knowledge of what the molecular shape will be. So down at the bottom of the slide, we see some common shapes for molecules that have 2 or 3 atoms connected to a central atom. And so we see that for 2 atoms connected, we can have a linear shape or we can have a bent shape. For 3 atoms connected, we can have what we call trigonal planar. So that's kind of a flat looking triangle. And then we have trigonal pyramidal. And so in that case, that central atom is kind of up a little bit from the 3 atoms that are connected to it. And then we also have something called T-shaped. And in that case, you have 3 atoms connected, but it literally looks like a T. And so what we're going to do today is we're going to talk a little bit about why we get these different shapes, even though we have, in the first case, 2 atoms connected to the central atom, and the second case here, 3 atoms connected. So the same number of atoms connected, but we wind up with different geometries, different physical shapes. So when we talk about the shape of the molecule, what we're really talking about for the most part are bond angles. And it's the bond angles and the bond lengths that determine the shape and the size of the molecule. So the bond length is more the size, the bond angle is the shape. And if you recall, that's one of the things you studied in the lab and saw some pictures of it as you did the computer program, and then measured bond angles, measured bond lengths, things like that. So one thing that influences the shape, obviously, is the number of atoms connected to that central atom. But the other thing is, remember we talked about when we drew our electron, our Lewis structures, that we had free electrons sometimes, those electron pairs that weren't part of any bond. And so those free electrons, those electron pairs, non-bonding pairs, and the electrons that are involved in a bond, you have repulsion of those. And so you're always trying to get the geometry that gives you the most space between electron pairs. And like I said, electron pairs count whether they're part of the bond or whether they're just free electron pairs. And that's what we kind of see on the picture on the right. We see that for whether it's linear or trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral, they're all trying to arrange themselves in a way that they have the maximum distance. So this idea is something that we call valence shell electron pair repulsion model. People rarely say the whole thing out. They usually use that acronym VSEPR, and that's usually referred to as VSEPR. So this VSEPR theory is what we use to explain the geometries of these molecules. So we're gonna talk about that a little bit more. So one big thing, and this helps us account for whether it's a double bond, a single bond, triple bond, free electron pair, is something called electron domains. And once again, that was one of the things you had to go through in the lab, is identify how many electron domains. And what this simply is just think of it as the directions in which the electrons point. So, and this counts whether it's, as I said, a single bond, a double or triple bond, a lone pair of electrons, free electrons on an atom. They all count as a domain. So in this example, this A connected to 3 Bs, this generic example, we would have 4 electron domains. So we'd have 1 for each of the A to B single bonds, we'd have one for the A to B double bond, and then we'd have one for that lone pair of electrons on the A. So in this case, that A would have 4 electron domains, even though we have 2 different types of bonds and we have a free electron pair on there, it's still they each count as 1 domain. So with the VSEPR model, what you're trying to do, as I said before, is give the best arrangement of those electron domains. And so remember, the domain doesn't matter if it's a free pair of electrons or if it's bonding electrons or if it's double bond or triple bond. Each of them count as 1 domain. You're trying to have the best arrangement, the best physical arrangement, so that you minimize those repulsions among them. So in other words, you're trying to get them as far away from each other as possible. And so these balloons on the right kind of give you some examples of what that kind of geometry works out to be. With the linear orientation for the 2, trigonal planar for 3, and then tetrahedral for 4. We're going to go through some examples of what these electron domain geometries are for whether you have 2 through 6 electron domains around that central atom. So once again, remember to determine the electron domain geometry, count the total number of lone pairs, single, double, triple bonds on that central atom. So each of those count as 1, whether it's a lone pair, a single bond, a double bond, or a triple bond. So if we have 2 electron domains, then we have a linear arrangement, and we see that here in our first example. And then we'd have a 180-degree bond angle. If we have 3 electron domains, then we have trigonal planar. And the way we get that name, trigonal planar, is you can see on the picture that there's been a triangle drawn connecting those 3 domains. And so it's all in a single plane, so it's flat in this case. And so because there's 3 sides to it, that's the trigonal planar name comes from that. And we see in this configuration, we have all of those bond angles are 120 degrees. So we've maximized the distance between the electron domains. For 4, we get tetrahedral. And so once again, we can see that you can draw this pyramid looking thing in there. And that allows us to have 109.5 degrees bond angles on each of these. So in tetrahedral, if you flip it around in that, it looks the same. And that name comes, anyway, it represents that. If we have 5 electron domains, then we see that arrangement, the trigonal bipyramidal. In that case, we have 2 different bond angles. In the plane of it, that's 120-degree bond angle, and then from the axial one to the in plane one, that's 90 degrees bond angle. And then the last one we'll look at is 6 number of electron domains. And in octahedral, and the octahedral thing comes from you have the 4-sided pyramid on top and 4-sided pyramid on the bottom, so it's 8 sides. Those work out to be, no matter how you orient it, it's 90 degrees between the electron domains. The other thing I'll mention is that sometimes people, instead of saying electron domains, call it a coordination number for the atom. for the purpose of this class, we'll stick with the name of electron domains. But if you do hear coordination number, this is what they're talking about. So we've got some electron domain geometries, but really that still doesn't tell us what the molecule looks like. It just tells us how the electrons would be arranged. So that what we really want is we would like to know the molecule's geometry. And so we can use some of this information that we get from the Lewis structures and the electron domain geometry. We can combine that information, and that can help us get to the actual molecular geometry. And so the difference between the molecular geometry and the electron domain geometry is that molecular geometry is really focused on the bonded atoms. So in this example for ammonia, if we wanted to figure out the molecular geometry, we would first go and we would write the Lewis structure that we think is appropriate. So in that case, we'd have the nitrogen with 3 hydrogens bonded to it, and then a lone pair of electrons on that nitrogen. So then we would go and think, okay, what's our electron domain geometry? Well, we would have 4 electron domains. We'd have the 3 that involve those single bonds of nitrogen to hydrogen. And then we'd have a 4th domain, which is that lone pair of electrons on nitrogen. So we'd have a total of 4. If we go back here, we know that if we have 4 electron domains, that it's a tetrahedral electron domain geometry. So we have that represented there with the kind of dotted line pyramid figure. And that shows us that we have that tetrahedral type shape based on the electron domain. When we do the molecular geometry, we only count the bonding electrons. In other words, the ones that are involved in a bond, from this case, from the nitrogen to the hydrogen. And that's what's going to, that electron domain geometry, by seeing that that's a tetrahedral, that's why we know it's going to be shaped not on a flat plane, so it's not trigonal planar, because of the impact of that free pair of electrons. But we're only interested in describing the geometry of the actual atoms involved. So that's why it's not tetrahedral, it's trigonal pyramidal. And we'll go through some tables there, which will explain this a little bit better, I think. So once again, let's go back and, based on the number of electron domains, talk about what the possibilities are in terms of molecular geometry for that particular electron domain. So if we have 2 electron domains, then the electron domain is going to be linear, and the molecular geometry is going to be linear. Okay, we don't have any other options there. The other thing is if you just had 2 atoms together, so in this case we have 3 atoms, but if you only have 2 atoms together, then that has to be, by definition, linear as well. There's no other way to arrange it. So if it's 2 electron domains or simply 2 atoms, that's pretty simple, it's linear. It's once we start getting to 3 and above that we see that we can have some of those lone pair of electrons, like we just saw in ammonia, and that can influence the molecular geometry. So once again, if we have 3 electron domains, we know from before that the electron domain geometry will be trigonal planar. And that's the first figure that we see there. If all of those electron domains are involved in a bond, then our molecular geometry is the same. It's trigonal planar. If now we have two of them that are involved in bonds, and one that's involved not in a bond, but as a free pair of electrons, and that's that NO2 minus that we see in the second example. What we see is that we get now what we call a bent structure, because those electron pair is there, it's not going to flatten out and be linear. And the reason for that is the repulsion between that free electron pair and the bonding electron pairs. And so that's why it doesn't flatten out and be straight, it stays bent. So even though you don't have anything there because it's electron, so there's no other atom to see, as we have in the one above, the trigonal planar for BF3. It doesn't flatten out because the free electron pair on that nitrogen impacts the shape because of electron repulsion. Let's talk about the tetrahedral electron domain. So in that case, there are three possible molecular geometries. We can have a tetrahedral molecular geometry, and that's what we find if all of the electron domains involve bonding pairs. We can have trigonal pyramidal if one of the electron domains is a lone pair, and then we can have bent if there are two lone pairs. So let's take a look at that. So once again, 4 is our number of electron domains. That electron domain says we start with a tetrahedral geometry. If all of those domains are involved in bonding, then the molecule will have a tetrahedral molecular geometry. If now, on the next example, 3 of those are involved in bonding, and one is a free pair of electrons, now we have trigonal pyramidal. So we still keep that core tetrahedral shape, but because one of them doesn't involve a bond to another atom, we have this trigonal pyramidal shape. And then finally, the third example is 2 of the domains are bonding domains and 2 are non-bonding, so that's free electron pairs there on the oxygen in this example. And so we start with that tetrahedral shape. We then only have 2 atoms bonded to the oxygen, and so that results in a bent shape. So one thing, let's talk about the non-bonding electrons for a moment, is that those non-bonding electron pairs, those lone pairs, are bigger than the bonding pairs. And because of this, the repulsion is greater, and this will change the bond angle. And so that's why, even though, for instance, it may be a tetrahedral electron, it may be electron domain geometry tetrahedral as we see this, as we go across the examples, the bond angles are going to change because the big blue lobe, which represents the free electron pairs, those will kind of compress some of the others because of that greater repulsion. And so we see an example of that here. We see for that first one, which is methane, there you have a carbon-hydrogen bond going on in each case. And so you kind of have uniform electron repulsion across that, and our bond angle is 109.5. For the ammonia, the NH3, because we have that lone pair of electrons at the top, and that's in the 2 red dots in the little loop there, that's kind of compressing the other ones a little bit. And we see that because of that repulsion, the bond angle actually has decreased by 2.5 degrees. So it's down to 107. And then the third example, which is water, in this case, we have 2 sets of non-bonding electrons, those lone pair electrons. And once again, those are the two red dots and the little loopy looking things. And so that kind of has even greater repulsion because now we've got two of those. And we see that HOH bond is compressed even a few degrees more down to 104.5. So going back to here for this tetrahedral example, so when we draw that molecular geometry, we don't really vary it off the tetrahedral. We kind of looks the same and we just kind of put in the blue balloon looking thing to signify the lone pair of electrons. But the reality is that the bond angles do change a little bit. And once again, if you go back and look at your labs, you would have seen that you saw some slight differences in some of these bond angles as some of this stuff occurred. So far, we've just, for the most part, focused on the single bonds, but double and triple bonds, which we know we can have larger electron domains than single bonds. Because of this, there's more repulsion going on there. And so what that does is, as we see this example, we see that the chlorine, carbon, oxygen, that bond angle is greater than, in this case, the chlorine, carbon, chlorine bond angle. So that double bond between the carbon and the oxygen, because it has a bigger electron domain than the single bonds of carbon to chlorine, it's kind of repulsing that a little bit more and giving itself a little bit more space, a bigger bond angle than the Cl-C-Cl bond angle. So one common theme you see in all this stuff is the electron domains like to get as far away from each other as possible. And you also have the attraction to the nucleus. And then you have, with atoms, you have the nuclei of the two atoms having repulsion. So we've kind of talked about that for a few lectures now, that you have these different competing things going on. And so that results in different bond angles, different bond lengths, things like that. So the other thing, remember, we talked about how with those Lewis structures, there are some instances where you don't obey the octet rule. So in other words, you have more than 4 bonds, more than 4 electron domains. And so let's talk about 2 possible electron domains that go beyond that octet rule. One is if you have 5 electron domains, and that's known as trigonal bipyramidal, and the other is if you have 6, which is known as octahedral. So for that trigonal bipyramidal electron domain, you have two positions in this geometry. You have axial, so in this figure, that's the 2 that are going up and down, and then you have equatorial. And equatorial, just think about the equator on the Earth. It's the ones in the plane going around. And so in this diagram, it's those 3 that form the triangle that would be on the flat plane. So axial and equatorial are the terms we use there. In this configuration, if we have any lone pairs of electrons, they will go on that equatorial spot, okay? So they won't go on the axial spot, they'll go on the equatorial. Associated with this electron domain geometry, you can have 4 different molecular geometries: trigonal bipyramidal, seesaw, T-shaped, or linear. And let's take a look at those. So once again, this is when we have 5 electron domains. That means our electron domain geometry is trigonal bipyramidal. Then off of that electron domain geometry, our molecular geometry is going to be driven by how many are bonding domains and how many are non-bonding domains. So in the first example, we have all electron domains or bonding domains. So in other words, we have atoms on all those 5 spots. So the molecular geometry is the same as the electron domain geometry. It's trigonal bipyramidal. The second example, we have 4 bonding domains. So we have 4 atoms attached, and we have 1 non-bonding domain. And remember, we said here that if we have a lone pair of electron for this trigonal bipyramidal electron domain, we're going to put it on one of the axial positions. So if we do that, so that's the blue kind of balloon looking thing, that's our non-bonding domain, our free pair of electrons. We have that, and then that configuration of those remaining 4 atoms attached to the central atom, that's called seesaw. So kind of like the playground seesaw that you used as a kid. The next example is 3 bonding domains and 2 non-bonding. So once again, we put those non-bonding domains on the equatorial plane, and that leaves us with a T shape for the central atom bonded to the 3 other atoms. And then our last example, we have 2 bonding domains and we have 3 non-bonding domains. In that case, all the equatorial domains are taken up with the lone pairs of electrons. And then we have the bonding electrons forming this linear 3-atom molecule. Let's take a look at the octahedral electron domain. So in the octahedral configuration, all the positions are equivalent. So what that means is the bond angles are the same, distance are the same, everything's the same. So those positions are interchangeable. So if you flip the molecule around or whatever, it's the same thing. There are 3 molecular geometries. One is the octahedral, second is square pyramidal, and third is square planar. So let's take a look at those. So here we have 6 electron domains, as we said, and we get that octahedral shape for the electron domain geometry. And if all of those are bonding domains, so in other words, if we have 6 atoms bonded to that central atom, then the molecular geometry is still octahedral. If we then go and substitute one of the bonding domains with a non-bonding domain, and that's the picture we have here, where we have a total of 5 bonded atoms. Then we have what we call square pyramidal. It doesn't matter where we put that non-bonding electrons, so that free pair of electrons. It doesn't matter which of those. I always think of these as like Tinker Toys, if you remember what those are. But if we substitute that balloon to any other spot on here, because these are all equivalent, it's still the same. It may look different, but if you had a model in your hand, you could see you could rotate it around, it's the same. So that's a square pyramidal. And then the third one is if you have 4 bonding electrons and 2 non-bonding, then you're going to have square planar. So because you want them as far apart as possible, they're going to be across from each other. So they wouldn't, if you have 2 non-bonding domains, they're not going to be next to each other, they're going to be across from each other. So that's the reason why it seems like maybe you would have more for this than not, but it's because on that square pyramidal, all of those are equivalent. And then when you get to the square planar, you want them to be opposite each other. So this kind of stuff here is nice. This tells us molecular geometry, but in reality, these are pretty simple molecules. It's one central atom and a few things off of it. Even if it's something like this where we have 6 things coming off of it, they're still relatively simple. The reality is that most molecules are bigger. So you still want to understand shape of those molecules and understand that geometry for the whole thing rather than just a small portion. And the way you do that is you go ahead and you go by central atom and figure out what that molecular geometry for that portion is, and then you kind of piece it together. So in this example, the black balls are carbon, the white balls are hydrogen, and the red balls are oxygen. And so what you would do is you would go through and starting here left to right, you would see that first one on the left, we have 4 electron domains, so it's a tetrahedral electron domain. There's no free pairs, no lone pairs there, so the molecular geometry is tetrahedral. The next one is a carbon double bonded to an oxygen and single bonded to an OH and then a single bonded to a CH3. So in that case, you have 3 electron domains and no free electrons. So that's a trigonal planar electron domain geometry and a trigonal planar molecular geometry. And then finally, in the last example, you have an oxygen bonded to a carbon and bonded to a hydrogen. So if we were to go and look at the Lewis structure for that, we would see that we actually have 2 lone pairs of electrons on that oxygen. And because of that, that means we have electron domain geometry, 4 electron domains, so an electron domain geometry, which would be tetrahedral, but 2 of them are non-bonding, they're lone pair. So that gives us a molecular geometry of bent. So that's how you would go about looking at what a bigger molecule like this, what its geometry is, and then you would kind of piece it together. And that's really one of the purposes of these like stick and ball models, is to try and give you a feel for what that overall geometry would be. So there's some homework problems associated with this. I'm not going to go over any of it. You guys can work on that. I'm just going to kind of move along, unless anyone has any questions about what we just covered. Okay. Let's go back to our friend polarity. So we talked about that in the last couple of lectures. Let's talk about that a little bit more. Because what we're interested in knowing is the molecule polar or not? And we tend to look at smaller molecules, a little more simple molecules, but at some point you want to look at bigger molecules. Just like we said just now, in terms of the shapes, we start by learning shapes of smaller molecules and kind of work our way up to bigger ones. It's a similar thing with polarity of molecules. We've been talking about it on a limited basis. Now we want to expand that out a little bit. So the first thing you ask yourself is it covalent or ionic? Remember, if it's a metal, non-metal, it's probably ionic. If it's non-metal, it's probably covalent. So then we've made our decision that it's covalent, for instance. And so then we go and we say, well, are the bonds polar? In other words, do they have a dipole? And remember, we talked about where if one of the atoms in the bond is more electronegative to the other, then we draw that little plus on the one that is less electronegative and draw the arrow pointing to the one that is more electronegative. So that's what we're talking about when we're talking about that dipole moment, so to speak. And so if we look at those individual bonds and we're looking at it and we're saying, well, there's not really much difference in the electronegativity of the 2 atoms, then we would say no, those bonds, none of them are polar, so it's a non-polar molecule. If we say yes, that the individual bond has a dipole, so in other words, one of those atoms is more polar than the other, has more electron negativity than the other, then we kind of look and see, does it balance itself out so that overall the dipole moment is zero? We'll look at a couple examples of that in a moment. If it balances that out, then it's nonpolar, even though it has polar bonds. If it doesn't balance out, then the molecule overall would be considered polar. So for a polar molecule that has more than two atoms, the dipole moment depends on both the polarities of the individual bonds and the geometry of the molecule. So this geometry of the molecule helps us determine if the polarities kind of cancel each other out, even if there is some polarity there. And once again, like I said, there's some examples coming up. Bond dipoles, dipole moments, these are what's called vector quantities. And a vector just means that the quantity has a magnitude. So in other words, it has a size or number associated with it, but it also has a direction. So when you talk about a vector, that's what you're talking about. You're talking about something that has magnitude and direction. And that's important in understanding if something is, a molecule is polar or not. Let's take a look at these two examples where we'll kind of get a feel for that direction and things like that. So in each case, we have molecules that have a central atom and then two other atoms bonded to it. So on the left, we have CO2, which we're saying is a nonpolar molecule. And why is that? So let's look at this structure that is here. So we have carbon double bonded to oxygen and double bonded to oxygen. So that tells us that we have two electron domains, right? Because if it's double bonded on each side to an oxygen, that satisfies the octet for carbon. So there's no free electron pairs on that carbon atom. So we remember from when we just looked at the molecular geometries that for this one, this would be a linear molecular geometry. We could go back and refer to our electronegativity table, and we could look up the electronegativity values for oxygen and carbon. And so that's the 3.5 under each of the oxygens and 2.5 under the carbon. And so then we can see that there is a dipole for each of those bonds. So the oxygen is definitely more electronegative than the carbon. So we do our little symbol of the plus on the carbon, the arrow pointing towards the oxygen to indicate that those are each polar bonds. This is where, even though we have two individual polar bonds, this is where that molecular geometry comes into play. Because think of it as if each of those bonds is a rope and the oxygen is pulling on the rope, they're pulling at the same amount. So they're basically canceling each other out. So even though you've got pulling on each side, because they're the same, they're pulling the same, and the overall dipole moment is actually zero. So you do have electron density shift, and we see that in the color-coded picture down at the bottom. But what we see is that they're kind of mirror images of each other. So things to the left of the dark blue line in the middle and things to the right, the colors are essentially the same. And that's because the oxygens are pulling the same amount on each side in terms of attracting those electrons. They're attracting them, so individually there's polarity, but overall there's not. So the molecule, while the bonds are polar, the molecule is nonpolar. On the right-hand side with water, we see that we have the oxygen is the central atom, and then a hydrogen, two hydrogens attached to it. In order to satisfy that octet rule, we know that there needs to be 2 more lone pairs of electrons on that oxygen. So in this case, we have lone pairs of electrons which are causing the shape. So it's not a linear shape anymore. And so because of that now, when we look at the polarity of the individual bonds, we see that it's going to go towards the oxygen because oxygen is more electronegative than the hydrogens. But instead of pulling against each other, like we saw on the CO2, it's actually kind of combining and having even more electronegativity towards that oxygen. So more sharing of electrons moving towards the oxygen. And so that gives us an overall dipole moment. And that's that kind of brighter red arrow you see kind of pointing up to the oxygen atom, is telling us that those 2 arrows going from hydrogen to oxygen on the right and left, those are kind of combining to have even a more polarity there. And we see that result of that in terms of electron density. We see that in the color-coded figure below it. We see a lot of red on top. We see a lot of blue on the bottom, and we kind of see that movement or that buildup of electron density as we go towards the oxygen. So here's a case of where in each one you had polar bonds, but the result, because of how things are oriented, is that one molecule is nonpolar and the other is polar. So these are a little easier to understand because there's only 3 atoms. When you get to bigger molecules, it gets a little more complicated, but you kind of go through the same process to figure out if overall the molecule is polar or not. Here's some more examples. So let's go through those. On the left, we have BF3. In this case, we know fluorine is more polar, has more electronegativity, more polar than boron. So we have the dipoles going out, but because it's of the geometry of it, where they're all kind of pulling equally, it winds up that it's nonpolar. The second one, HCl, hydrogen on the left, chlorine on the right. Once again, that dipole goes towards the chlorine, and it's just going in one direction. So overall, the molecule is polar. The next one, CH3Cl, we have really the CH bonds. There's really no significant polarity difference there, no electronegativity difference there. So there's no polarity going on there. But from the carbon to the chlorine, we have polarity there, electronegativity difference. So overall, that molecule is polar. And then in H3, we have those nitrogen, which is more polar, more electronegative than the hydrogens. We have all of those coming in towards there. They're kind of building upon each other. Overall, the molecule is polar. And then finally, CCl4. So with that case, we have polar bonds in terms of the carbon-chlorine bonds, but because of the geometry of things, they're all kind of pulling equally and it kind of cancels out. So we wind up with a nonpolar molecule. So here's some examples of where you have polar bonds going on, but because of the molecular geometry, you wind up with an overall nonpolar molecule or a polar molecule. Okay, let's move on to valence bond theory. So in valence bond theory, you have electrons from 2 different atoms and they're starting to occupy the same space. We call this an overlap of orbitals. And so as the space is shared between the electrons, we get our covalent bond. And so here we have some pictures of that. So in the first one with 2 hydrogen atoms coming together, we have two 1s orbitals, and we see an overlap there of the electrons. That's how we represent the electrons coming together. That's the overlap you see, where it's a little bit darker blue there. And so that's the two 1s orbitals overlapping. The next one with HCl, that valence electron on the chlorine is a 3p electron. And so that's the shape that we're representing those p electrons with. And then it overlaps with that 1s orbital from the hydrogen. And once again, you can see kind of like that bluish, pinkish overlap area there. And then finally on Cl2, we have overlap of 3p electron with 3p electron. So as those orbitals overlap, we see this kind of dark pink overlap of those lobes. So this is what we're talking about, this overlap, and that's how we represent the formation of the bonds. So in valence bond theory, the atoms are trying to get to the spot where you have the lowest energy. And the lowest energy means you have the least amount of repulsion. So in other words, like charge repulsion, which can be electron-electron repulsion, or it can be the positive nuclei repulsing each other. And then you want the maximum electron nucleus attraction. So you're kind of balancing all that stuff out. If they get too close, the nuclei don't like it. If they're too far apart, you don't have that electron nucleus attraction optimized. If they get too close also, you get more electron repulsion. So there's like a sweet spot there. And that's what this energy diagram on the bottom is showing you, is that on the right-hand side, they're a little too far apart. The one in the middle, excuse me, they're getting closer. And then on the third one, where you have that overlap, which we just kind of talked about, in this case, assume these are, because it's hydrogen-hydrogen, we know it's 1s orbitals overlapping. We get to that sweet spot, and that's where we get to that balance between attractive and repulsive forces. And then if we go closer, then we see the energy goes up again because we're getting that nucleus-nucleus repulsion. So for these different bonds, you have kind of this sweet spot where you minimize the energy as you balance out all these repulsion and attraction forces that are taking place. So this leads us to something called hybrid orbitals. And so hybrid orbitals form when we'll call it mixing of atomic orbitals to create new orbitals of equal energy. Remember, we had talked before, when things are at equal energy, that's called degenerate. So these hybrid orbitals are degenerate orbitals. This process of kind of mixing these atomic orbitals from one to another we call this hybridization. So the whole idea of hybridization is a math thing, which we're not going to worry about. But we will talk a little bit about the terminology of hybridization. And like I said, I think the key for you to remember is that these orbitals, these hybrid orbitals are of equal energy, and so they're degenerate. So when we have two orbitals that hybridize, they create two new orbitals that are like a combination of the two. If three mix, then we create three orbitals that are mixture and on down the line. So let's look at beryllium and sp hybridization. So we're going to combine an s orbital and a p orbital here. So if we look at the orbital diagram for beryllium, we see, and that's the first electron configuration that we see down there, the top one. We see we have one s2 and two s2 electrons. Beryllium makes electron deficient compounds with two bonds for it. And why is that? Well, that's because we get sp hybridization with beryllium. What that means is we mix one s orbital and one p orbital, and that's the second electron configuration that we see. And it results in that hybridized orbital that we see on the bottom. So we have two 1s electrons, and then we have two sp electrons. So those sp electrons are what we're calling the hybridized orbitals, the hybridized electrons, and that's where the bonding is going to occur. So when we talk about mixing these, in this case, s and p orbitals, to give us two degenerate orbitals, they're really the hybrid of the two orbitals. So if we look at the picture below, we see the blue circle, the blue sphere, which is what we're representing our s orbital with. And then we have the two lobes, which we're representing a p orbital with. And then if we combine those, so in other words, think of that s orbital going on to one of the lobes of the p orbital, we would get two hybrid orbitals. And that's what you see written after that. And so the two sp or hybrid orbitals. So basically think of it as you've increased the size of one of those lobes where the s orbital is now interacting with it. Since you have two sp orbitals, if you superimpose those, you get what just looks like a bigger p orbital. Because in this case, we're not factoring in the small lobe, just the big lobe. So when we talk about positioning these sp orbitals, so because the two orbitals are degenerate, they would want to be 180 degrees from each other. So in other words, we look at these lobes here on this beryllium F2 molecule, and we think of the Vesper model, we see that it's going to be linear. So in this case, we have the fluorine, its 2p orbital is overlapping with the sp hybrid orbital for beryllium. And we see that on each case because we have the two fluorines that are coming in like that. Let's look at sp2 now, hybridization. So in sp2 hybridization, that would be one s orbital interacting with two p orbitals. And once again, so we draw our s orbital as the sphere, the two p orbitals as these two different orientations of a p orbital. And that leaves us with three hybridized sp2 orbitals. So in each case, we have that bigger lobe going to one corner of the triangle, and we wind up with this sp2 hybridization of the three orbitals shown there with kind of the triangle shape with the larger p-looking orbitals. Okay, let's look at sp3 hybridization. So if we use carbon as the example there, once again, we have one s orbital, that's the sphere. Then we have the three p orbitals. So those three p orbitals are going along the x, y, and z axes. And so then we have that hybridization along the different axes as well. And that results in the four orientations that we see there. We combine those all together and we get this tetrahedral looking figure down at the bottom. Let's take a look at water and see what happens with water. If we draw a Lewis structure and associate it with Vesper, it has a bent shape. If we look at the oxygen in water, its electron configuration is 1s2, 2s2, 2p4. If it shares 2 electrons to fill its valence shell, they should be in 2p. So why wouldn't that make the angle 90 degrees? Why is it 104.5? Well, let's take a look at that. So as we said, oxygen has 2 bonded and electron domains and 2 lone pairs, so it has 4 electron domains. Because of these 4, that means the hybridization is sp3. So, and remember we talked here, going back here for sp3 hybridization, we wind up with that tetrahedral shape. And so in tetrahedral shape, your bond angle would be 109.5. We said here it's 104.5. If you recall, when we talked a little while ago, we also said that these non-bonding electrons kind of push things and change that bond angle a little bit. So that's another reason why the bond angle isn't exactly a tetrahedral. You kind of get that compression, so to speak, about it because of these free electrons. So it's a combination of the sp3 hybridization and then the fact that 2 of those are non-bonding electron pairs. So we had talked before about hypervalent molecules, and those are the elements, those are the ones that have more than an octet. So in that case, the valence bond model would use d orbitals to make more than 4 bonds. And this works for period 3 before and lower. So remember, the periods are the rows. It's a little more complicated than that, and we won't get into that in this particular class. So let's talk about hybrid orbitals, kind of summarize what we talked about. So we would draw a Lewis structure. We use Vesper model to predict the electron domain geometry around the central atom. We would specify the hybrid orbitals needed to accommodate the electron pairs based on their geometric arrangement. And if you recall in the lab, we did some of this where we said, is it SP or SP2 or SP3 or whatever, and then link that to the geometry. For SP, if that's the hybridization, then we'd have 2 sp orbitals. That's a linear geometry. If it's s with 2 p orbitals, then we have 3 sp2 orbitals. And that's a trigonal planar geometry. If it's s with 3 p orbitals, then we'd have 4 sp3 orbitals. And we get to the sp3 tetrahedral orientation. Okay, there's some homework problems associated with this. I'll let you guys work on that. And we're going to move on to types of bonds, unless anyone has any questions about the last part. Okay, so for types of bonds, let's talk about how triple and double and triple bonds form. And if we only talk about hybridization, it's difficult to describe what's going on with double and triple bonds. If we use the orbitals that are not hybridized, we can have what we call a sideways overlap. And we'll see some pictures of how that's represented, which I think will make it a little easier to understand. There's 2 types of bonds. There's the sigma bond, which represents the single bond. And there's pi bonds. And pi bonds are what make up the double and triple bonds. So sigma bonds are characterized by head-to-head overlap. And you see that down on the bottom there with those 2 p orbitals overlapping to form a pi bond. It goes along the internuclear axis. So in other words, the internuclear axis is the axis, if you drew imaginary axis between the 2 nuclei of the atoms that are bonding together. And that's where the single bond, the sigma bond, is. The pi bonds have a sideways overlap. So in other words, you see that the electron density is above and below that internuclear axis. And so the pi electrons are above and below that sigma bond axis, and that's what forms the pi bonds. So as I said, single bonds are always sigma bonds. Multiple bonds have one sigma bond, and then the other bonds are pi bonds. And so let's see if we can kind of sort through some of this picture here. So the one on the left is C2H4. So you can sort of see the little carbon, little C in the middle there. So that's supposed to represent a carbon. Those are carbon atoms. And then you have two hydrogens coming off. We'll see that that's the blue in the second one as you go down. So the first picture is just showing the carbon bonded to the carbon. So that initial sp2 hybrid orbitals bonding together, okay? And then you've got two coming out the back there. Then the next is you've added the hydrogens on, that's the blue circles onto the purple. So that's supposed to be the 1s part from contribution from the hydrogen onto the carbon. And then finally at the bottom, the pink electron density above and below the purple sigma bond, that's supposed to represent the pi bonds. So in that case, what we see sigma bonds from the carbon to the hydrogens. And like I said, there's 4 hydrogens there. And then the sigma bond from the carbon to carbon. And then the pi bonds from the carbon to carbon. And the pi bonds, that represents the double bond. On the right-hand side, that's C2H2. And so it kind of starts out the same, where you have some hybridization in the beginning. Then you add your hydrogen to it, that bond. And so at the end, now you have 2 sets of pi bonds going on. So 2 carbon-carbon pi bonds. And so you see it vertical, kind of like in the one on the left, and then you see one on the horizontal plane as well. If you look kind of close, you can see it coming out the back there. And so that signifies that there's a triple bond there. So you have the sigma bond and then the 2 pi bonds for a total of 3 bonds. So the one on the right is carbon triple bonded to carbon, and then each of those carbons having a hydrogen off of it. The one on the left is carbon double bonded to carbon, and then 2 hydrogens bonded to each of the carbons. So it's a little tricky to sort through all that. So it's probably worth taking a little bit of time and looking at it so it's clear to you. So when we talk about electrons, we tend to talk about localized or delocalized electrons. So bonding electrons that are specifically shared between 2 atoms, and this is whether it's a pi bond or a sigma bond, those are called localized electrons. A lot of times we can't describe all the electrons that way. Remember, we've talked a little bit about resonance. And these electrons that are shared by more than the 2 atoms, so several atoms share the electrons, these are called delocalized electrons. So let's talk about that a little bit. Here's a graphical representation of benzene. So if you recalled in the lab, we did some measurements and things like that in terms of the bonds, and it didn't really match up with a single or a double bond. And that's because of delocalization of the electrons in resonance. And so if you kind of follow the picture, so you have the sigma bond, and then you also have those p orbitals. And so if we go down to the bottom presentation, we see that those C bonds are written in terms of having the pi bonds localized. So remember, localized is you're just sharing the electrons between the two atoms. The reality is that they're not localized, they're delocalized. And so then that leads you to this resonance structure over to the right at the bottom. So in other words, you kind of fill in the electrons as you go around to kind of show how it shares. So that's what we're talking about with localized versus delocalized electrons. The localized are just between the two atoms. The delocalized kind of smear out, so to speak, and get shared by multiple atoms. Okay, let's talk a little bit about molecular orbital theory. So a few chapters ago, we talked about how wave properties are used to describe the energy of the electrons in a molecule. So that brings us to something called molecular orbitals. So far we've been talking about atomic orbitals. And so now the molecular orbitals have a lot of the same characteristics as atomic orbitals. You have a maximum of 2 electrons per orbital. The electrons in the same orbital have opposite spin. They have definitive energy levels, and you can kind of visualize electron density by contour plots. The big difference is that they don't just represent a single atom. They represent the entire molecule. So whenever 2 atomic orbitals overlap, 2 molecular orbitals are formed, one bonding and one anti-bonding. The bonding orbitals, it's a constructive combination of the atomic orbitals. And this means that it's going to be more stable. And if it's more stable, we know it's going to be a lower energy. The anti-bonding orbitals are a destructive combination, and that means they're less stable and at a higher energy. They also have something called a nodal plane, and this is the place where the electron density is equal to 0. So we'll see that visually here in a moment. So let's take a look at this. Here we have 2 1s orbitals overlapping, so to form H2. So the bonding orbital is called sigma. The anti-bonding is sigma with the little asterisk or star over it. And so visually, I think it's easier to see than probably the description was. If you look on the right-hand side there, you see in that bonding molecular orbital, you've got electron density concentrated between the nuclei. So in other words, you have that bond formation. In the anti-bonding molecular orbital, that's where we have that node there, that nodal plane that we talked about between the nuclei, and that tells us that there is no electron density there. So in other words, nothing's going on there. When we draw molecular orbital diagrams, we draw something called an energy level diagram. And this shows how the atoms combine to form molecular orbitals. So once again, using our H2 as the example, on the left-hand side, we have what that looks like. Its electron configuration, 1s electron. We have the same thing on the right-hand side from the other one. The spins are reversed. And so then they combine, and the molecular energy level diagram, they combine, and that's that sigma 2 1s that you see labeled there. So that's the H2 molecule. And then the anti-bonding, because there's no more electrons left, that's empty. So we can calculate something called a bond order, and we do that by taking the number of bonding electrons, in this case 2, minus the number of anti-bonding electrons, in this case 0, and then multiply that by half, and that tells us there's one bond there. Let's ask ourselves, can He2, can 2 helium atoms combine? If we look at this, once again, helium has 2 electrons. So we have 2 1s electrons on the left, 2 on the right. We first fill the bonding molecular orbital down at the bottom. Then we have 2 electrons left. So we fill, the anti-bonding. And what we see is that 2 minus 2 equals 0, times a half is 0. So that means it cannot exist. So in terms of the principles for the formation of molecular orbitals, the number of molecular orbitals equals the number of atomic orbitals combined. Atomic orbitals combined with atomic orbitals of similar energy. The effectiveness with which the 2 atomic orbitals combine is proportional to their overlap. As the overlap increases, the energy of the bonding molecular orbital decreases. Each molecular orbital accommodates at most 2 electrons with opposite spin. So that's the Pauli exclusion principle, once again. And then molecular orbitals of the same energy are populated. 1 electron enters each orbital before they pair. That's, once again, Hund's rule. So I'm going to quit there. We're out of time. We have a few more slides to go. We'll finish that up next week. Just to remind everyone again, exam on Monday on chapters 7 and 8. And then in terms of the lab final, those of you who are in my section this afternoon, that's an online final. Those of you who have other instructors, if you have questions about it, please contact them. All right, thank you.
So, Professor, I have a question about the finals.
Okay.
So for your lecture final, it's the same as like our regular finals, but it's like over everything. So if we were to not take that final, would our grade still be just the others, and that would be considered the dropped final?
No, you can't drop the final.
So that one we do have to take.
You have to take the final, yes. If you don't take the final, you'd get a 0.
Well, I was referring to the lab portion. I'm unable to go in person for Namani's, and he hasn't responded about me taking like an online version of it. So if I don't take that final, would my grade just stay where it is?
So what are you, Thursday? Is his section Thursday? I forget.
Yes, my final for him is tomorrow.
Okay. So here's what I'll tell you is if you don't hear from him by, what time is your class?
It's 1:30 tomorrow.
1:30. Okay. So hopefully he'll respond to you today. If he does not respond to you today, send me a message tomorrow morning and I will set up an online exam for you.
Thank you.
Okay.
Bye.
But I would hope that he would respond to you today. But if he doesn't for some reason, send me a message in the morning, copy him in on it also, and then I'll just go ahead and I'll give you one of the online ones that I'm giving my sections. Or something similar, it may not be exactly the same, but similar. Okay?
All right, thank you.
All right, thanks. Mm-hmm. Does anyone else have a question? Okay, thanks.